In this section, we will derive the minimum mean square error, or MMSE, MIMO equalizer. Recall we have the basic channel model where we send the streams and we collect them in a vector X for each carrier associated with each transmit antenna. H is the channel H matrix, and N is the noise vector, which is the noise added to each received chain, and Y is a received signal. So for a 2x3 system, Y will be a 3x1 vector, N will be a 3x1 vector, X is a 2x1 vector, and the H matrix is a 3x2 matrix. Again, these equations are valid on a per carrier basis, especially since in MIMO we're talking about flat fading, and OFDM will provide flat fading on a subcarrier basis over a frequency selective fading channel. Now let's assume that we estimate X using the matrix W. So given Y and knowledge of the H matrix, we want to estimate X, and let W be the matrix such that the estimate X is equal to W times Y. So we operate W on the received vector Y to obtain an estimate X of the transmitted carriers for each spatial stream. The key is that we want to find the optimum matrix W in the minimum mean square sense. So we need to minimize this expression over here. So we take the expected value of X minus W times Y, which is the error between the estimated X and the actual transmitted X. The Hermitian of that times X minus WY. This gives us the minimum mean square error. We are interested in the matrix W that minimizes the minimum mean square error. So if we take the Hermitian inside, we get X Hermitian minus Y Hermitian W Hermitian. They get swapped times X minus WY. We multiply through and we get this expression here. Now if we look at this expression here, we will take the derivative with respect to W and set it equal to 0 to find the optimum W. So if we take the derivative of this expression here with respect to W, we obtain the expression here, minus 2x y Hermitian plus 2 wy y Hermitian. And in obtaining this expression from the expression shown here, we are using these identities, which are available in the matrix cookbook that we referred to earlier in the derivation of the zero forcing equalizer. So when you have terms where B and C are constants, and we're taking the derivative with respect to the matrix X, and we have B transpose X C, we take the derivative, we get this expression over here. And where we have cases where we only have X transpose with the constants A transpose X transpose B, we get the expression here. So if you use these identities and go back and take the derivative with respect to W, then we get this expression here. And if we take in the expected value, we get the expected value of X y Hermitian, which is actually the cross correlation between the vector X and the received vector Y. And we also get the expected value of y Hermitian, which is the autocorrelation matrix for the received vector Y. So we set this expression to 0 and take the expected value. We find for W is equal to RYY inverse times RXY, where RYY is the autocorrelation, the expected value of YY Hermitian, and RXY is the cross correlation. So the matrix W derived in this fashion is the minimum mean square error solution and is optimum in that sense. And by the way, this does not imply that it is optimum in the sense of the MIMO, the best MIMO equalizer. We'll get to that. That will be the maximum likelihood equalizer. And this is only true for open loop systems. In closed loop systems, it's a different formulation, and we can actually get better performance using singular value decomposition, and we'll get into that. But in the sense of minimizing the mean square error, then this equation for W is the optimum solution in that sense. So let's compute what RYY is. So Substituting for y, we get that y is equal to hx plus n times the Hermitian of hx plus n, and if we take in the Hermitian and multiply through, and then we move in the expected value, and note that the noise is additive white Gaussian noise, and the noise in each receive chain is independent of the noise in the other receive chains, and the noise is zero mean. Then when we take in the expected value, obviously this term drops out. This term also drops out, and the expected value of nn Hermitian is just a diagonal matrix sigma n squared times in. Now, as we take the expected value into this part of the expression, we are going to assume that the carriers in the transmit chains are also independent identically distributed at zero mean, so that the expected value of xx Hermitian is a diagonal matrix equal to sigma x squared, where sigma x squared is the variance of the carriers. So keep this in mind, that we've actually made an assumption on the actual carriers also, in addition, of course, to the valid assumption on the noise. And this is highlighted in the paragraph over here. Now, if we compute the expected value for the cross correlation Rxy, again substituting for y, notice that since n is zero mean white Gaussian noise for each receive chain, then of course the expected value of x times n is 0, and we get that Rxy is equal to sigma x squared h Hermitian. Recall that W for the minimum mean square error equalizer was equal to RYY inverse times RXY, which is of course the famous formula. And substituting for RYY and RXY, then we get the expression shown over here. In this expression, we're factoring out sigma x squared. So if we bring out sigma x squared, we get 1 over the signal to noise ratio over here, which is shown here. And of course, the sigma x squared terms cancel out, and we get this expression, which is very nice because we highlight the effect of the signal to noise ratio. Now let's examine this expression for a little bit. If the signal noise ratio is very high, then this term goes to 0, and we're left with W equal to H Hermitian H inverse times H Hermitian, which is exactly the expression for the zero forcing equalizer that we derived earlier for open loop MIMO systems. This shows that for the case where we have high signal to noise ratio, the performance of the minimum mean square error MIMO equalizer is equivalent to the performance of the zero forcing MIMO equalizer. However, when the signal to noise ratio is low, then this added term here gives a definite advantage to the performance of the MMSE equalizer over the zero forcing equalizer. So at lower SNRs, we observe a gain by using the more complex minimum mean square error equalizer. And this is very important, since the zero forcing equalizer basically ignored the noise in its derivation, whereas the minimum mean square error equalizer incorporated the noise in its derivation. Here we just give a general outlook on the definition of a maximum likelihood equalizer for MIMO systems. So if we take a look at this expression here, the maximum likelihood estimate of the transmitted vector is obtained as follows. If we obtain the distance between the received vector and the message S transmitted through the channel, then here we're showing the distance between the received vector and the transmitted message S. And if we calculate this distance for all possible messages S, and then pick the S in which this distance is the minimum, that will yield the message SML, which is the desired result for the maximum likelihood decoder. Now obviously this implies a huge amount of computations to actually calculate the distance based on the received vector Y and all possible transmitted messages S, and to actually calculate all these distances and then go through and find the one with the minimum distance, and that will be the maximum likelihood distance. That of course is involves a lot of computations, so there are a lot of interesting papers published in the literature that provide means for implementing the maximum likelihood MIMO decoder so as to minimize the number of operations, and in some cases some approximations are made in which a dramatic decrease in computations is achieved but at a slight deterioration of performance. So if you're interested in maximum likelihood decoder for MIMO, please refer to the literature. Later on we're going to show performance curves which show the performance of a maximum likelihood equalizer compared to, for example, zero forcing, and also compared to closed loop SVD MIMO systems, and some interesting results will be highlighted in those comparisons. I refer you to this reference by Qingwei Li and Wang on the improved K-best sphere decoding algorithm for MIMO systems that reviews the sphere decoding techniques and the other techniques that are available up to 2006, and proposes an improved technique. So there are methods in which maximum likelihood detectors can be implemented in VLSI. However, the complexity is still high, but as we have shown, there is considerable improvement in performance compared to MMSE or zero forcing maximum likelihood detectors, so it is well worth investigating in terms of the architecture and its complexity.